We are live now.
Hi, Joseph.
Hello. Hello, Ashwin. Welcome.
Joseph, can you hear me?
Yeah, I'm able to hear you.
Yeah, Joseph, can you please continue?
Yes, yeah.
Okay.
I'm able to hear you. Okay. Shall we start? Kamal sir, shall we start? Maybe.
Yeah. Maybe one or 2 minutes.
Yeah. Okay. Yeah.
Few
Students
more
are joining.
participants
Yeah.
join.
Yes. Fine.
They will miss the introduction. Joseph, maybe we can go ahead.
Yeah, sure. Good evening to one and all. Respected Professor Sunil Mukhi, respected Professor H.S. Mani, and other senior faculties, and our Sunday class students and scientists, and the participants. I wholeheartedly welcome you all for this Professor SVM Satyanarayana online memorial lecture. Today, our respectable Professor Sunil Mukhi graciously agreed to give a talk on remarkable outcomes of mathematical physics. As an introduction, now I invite Dr. C. Rubala, who is also our Satya sir student. She is now working as a scientific officer in NIT Trichy. So she will give a introduction about this lecture series. Invite Rubala.
Thank you, Joseph. Good evening, respected professors and dear friends. It's a great honor to introduce Dr. SVM Satyanarayana's Memorial Lecture Series to this audience of dedicated physics learners and passionate students of Satya sir. We had the first memorial lecture on the most favorite topics of Satya sir, which was on entropy, and it was delivered by the distinguished physics professor, Dr. Deepak Dar. This first memorial lecture we had on 21st of January. Today, we are here to listen to the second lecture in this series, and this talk is on Remarkable Outcome of Mathematical Physics by Dr. Sunil Mukhi, the Honorary Professor and Raja Ramana Chair Physics at IISER Pune. Again, this topic also is something that he always had close to his heart, like how theoretically we need to model things in order to appreciate our understanding about physics and the day-to-day aspect of it. Like he used to tell us how he was, when he learned classical mechanics during his masters, he was using the Lagrangian mechanics to model and understand some of the natural phenomena through his that was the first time he's encountering classical mechanics. And with that concepts, he was trying to model something which is very complicated to our understanding. So that was how Satya sir was traveling right from his UG and PG days. And this lecture series has been conceived as one of the ways to remember the legacy of Satya sir, to bring together some of the phenomenal people like our Deepak sir and Sunil sir to this platform where we can reach thousands of students and who have a very much thirst for learning physics and appreciate the subject in its full glory, which is what in all the Sunday classes that sir was trying to do to us. And this was one of the visions of Satya sir, that his students like us, we take forward activities in terms of physics teaching and learning. And I see this memorial lecture as one such attempt. And we are very grateful that such eminent physicists are accepting to come and join us on this platform and sharing their valuable knowledge with us. And before I conclude these remarks, I take few minutes to share some of the attributes of Satya sir, which will be an inspiration to many of the young audience here. Satya sir was like a lighthouse to us. He lived as a life which inspired many of us. And the first important thing was he never waited an opportunity to come to his doorsteps. He created the opportunity, and then through that he executed all that he wanted to do. And one such attempt was a Sunday class. He was then a research scholar at IGCAR, and he opened this platform at the STTP in IGCAR, and then he moved on to the Madras University. So he did not wait that he will complete all his degrees, UG, PG, PhD, postdoc, and then I'll come back as a full-fledged equipped teacher to handle classes. Rather, at all the times, even he used to share when he was in RIE Mysore as a PG student, he used to teach his seniors. So that was the kind of platform he created always for himself. And I think that is one striking thing, that us young kids here who are in their beginning of this journey, don't wait for all of this to get over to equip yourself. Just keep, for example, today we listen to this remarkable outcome of mathematical physics from sir, and then we go and discuss about this in Monday among our peer group, be it a faculty, be it our students. We can talk and discuss about this, and this is what sir was continuously doing. He continuously sculpted himself throughout the journey, and he never waited for the destination so that he will reach the destination and then he will start doing his activities. So that was one of the signatures. And the second aspect that I wanted to share was about the active learning strategy that sir was engaging towards the 2021 onwards. Like it was, I think, PTTS 2021, where they had a session with a Nobel laureate, Carl Wieman. He is one of the pioneers in active learning strategies. So they had a session of how, apart from the passive lecturing mode, how to engage the student through questioning, processing the concepts, and then take away something at the end of the session. And even I think when he was diagnosed in the cancer towards the 2022 on, so he penned down a note on the pedagogy of physics teaching, and where he had a notes about how you can handle an introduction to the electrodynamics class. So he posted a kind of possible questions a student can have and how you will be addressing. So this was some attempt that he was trying to do at the end of the 2021 and 22. So I think as this platform is something which is opening up for all of us, we would look forward to engage more such teaching, learning, pedagogy also come inside, so that it will take forward the torch that sir has shown to us. And So that notes was the question, the answer. That was what he has written about this electromagnetic introductory classes. And so he begins the writing like this. What is the role of a teacher? I understood that more than teaching certain content or cover syllabus, role of a teacher is to prepare a student to learn. Learning is a lifelong process. If we prepare the students to learn, they will learn on their own. He was all the time only doing this to us. He never wanted us to clear net, clear gate. Rather, he was always equipping us to be a good learner wherever we are going to be. And then he ends the article with a quote from Aristotle. The mark of an educated mind is to able to entertain a thought without accepting it. And this is resonating with what Sir calls as intellectual discomfort. He always wanted us to be in intellectual discomfort so that we keep questioning what we are said inside the class, or even whenever he lectures, he says, don't just accept it just because it is coming from me. Question it, and that discomfort will actually enable you to understand concepts better. So with this, I end my note emphasizing that vision of Satya sir is on reformations about the teaching and learning strategy. We have with us Dr. Jayabalan. He's from the University of Duisburg-Essen. He will be teaching on quantum mechanics. So almost from 2021, Joseph Prabha has been coordinating with a lot of the extended Satya sir family, and he has been making it happen, and with the efforts of Kamal sir and other our Sunday class people. And this Sunday class, which is free, is happening on different subjects. Currently, it is mathematical physics and quantum mechanics. And I think this is the success of Satya sir, that we students have taken forward his light, and we are trying to shed across in all possible ways. And I'm very grateful that I had a chance to travel along with Satya sir since 2009. And I'm thankful to the professors who have accepted to be with us. I thank Professor H.S. Mani, who has been also identifying good speakers for us for this memorial lectures. And thank you. I welcome you one and all for this second lecture series. And I really wish that we all who are participants of this will take away this lecture series in some kind of writing and other form, so that it gets recorded in multiple ways. Thank you very much. I welcome you, sir.
Thank you. Thank you very much, Rubala. So now I invite Dr. Kamal, who is a senior scientist in RRCAT Indore. So he will play a short video of biography of Satya sir.
Professor Mukhi, if you can stop sharing, we will put it only 5 minutes of video. Yeah.
Yes, I've done that.
Thank you.
But if it is satisfying only 1, 2 and 3, then that is called a monoid. These are just names for they exist, so I am writing. And if it satisfies 1, 2, 3 and 4, it's called a group. And if you may want to call it as a 5, if it satisfies 1, 2, 3, 4 and 5, it's called an abelian group. Learning science is not about answering a question, but it is a training to question the answers. I believe that we must judge the progress of a student not on the basis of answers that he writes in the examination, but only on the basis of questions that he asks in the class. Because the ability of questioning gives us a window to judge the understanding ability of the student. So I think, in my opinion, the first and important aspect of teaching is to make them ask questions. Now, this is a very, very tough task. We have a group of heterogeneous people with different backgrounds, different knowledge initial states, and we cannot easily make everyone to come out in open and ask questions. There will be a lot of inhibitions, there will be fear, there will be a doubt that others will ridicule. All these problems will be there. But we have to deal with all of them. We have to live with all of them, and yet make some progress in terms of training them to ask questions. This is the only way to really judge whether someone is making a progress or not. Second important thing is how best you teach does not depend on you alone. It depends on you as well as the given set of students. So your teaching should be a function of the group who is attending. Suppose I learnt group theory. I teach everywhere in the same fashion, but the audience in one place may be different from the audience in another place. So your teaching, the content, the method of presenting, and the problems that you choose, the way you present it, everything has to be a function of the set of students or the audience whom you are addressing. So if the audience are ready to receive, then only they will receive. How much ever clear presentation that you make, if the audience have no readiness, then it all goes waste. Now, for that purpose, what we have to do is you have to do an initial exercise of making the audience ready for what you have to teach. Okay, so how to make audience ready is another technical aspect which we will discuss. So you have to have a readiness. If you are not ready to receive, you will not receive.
Thank you, Dr. Kamal. So now I invite Dr. Ashwil to introduce our honorable speaker, Professor Sunil Mukhi.
Thank you. So, Professor SVM Satyanarayana, affectionately known as Satya by his students and friends, was more than an academic mentor. He was a beacon of knowledge and pillar of support, a true master of the art of teaching, a revered educator, and a beloved father figure to countless students, including me. I had the privilege of completing my PhD under his esteemed guidance at Pondicherry University. And this is the second talk of the memorial lecture series going to be delivered by Professor Sunil Mukhi. Professor Sunil Mukhi is Honorary Professor Emeritus and Rajaramana Chair Physics at IISER Pune. Professor Sunil Mukhi has a PhD in theoretical physics with a specialization in quantum field theory and supersymmetry. He completed his PhD from Stony Brook University, USA. He held a postdoctoral position at the International Center for Theoretical Physics, Trieste, Italy, and was a faculty member at Tata Institute of Fundamental Research, Mumbai for 27 years, where he held various posts like senior professor, dean, graduate students, and dean graduate studies and chair Department of Theoretical Physics before joining IISER Pune as honorary professor emeritus. Professor Sunil Mukhi's research addresses fundamental properties of the theory of quantum fields and strings. With this short intro, I would like to welcome Professor Sunil Mukhi to deliver his talk on remarkable outcomes of mathematical physics. Thank you all for giving me this opportunity to introduce Professor Sunil Mukhi. Over to you, Joseph.
Thank you, Ashwil. So now I invite our respected chief guest to deliver his talk.
Thank you so much. I hope you can hear me well.
Yes, sir. Yes, sir.
Okay, I will share my screen again. And good. I hope you can see this now.
Yes, sir. Yes, sir. Yes, perfect.
Okay. Well, let me start by saying it's an incredible honor to be speaking in this series. Thanks to Professor Mani, I got involved in this. And of course, Professor Mani is a very old friend of mine. And I was sort of enlightened about the role of Professor Satya and his activities. And I was sent some material, which I have also read. And today we saw a beautiful YouTube video, which communicated what sort of person he was. And I have to say that this is a really inspiring person. Even some of his thoughts that I saw today about preparing the audience to receive your lectures when you teach, it struck me as a new thought, which I probably missed. And I feel that I can use it to make my teaching here at IISER Pune better in the future. So I will start by dedicating my talk to him and to his own selfless dedication, which inspired so many generations of students to physics. I think particularly I'm also very, very impressed by the emphasis that he placed on social justice and the fact that people are passionate to study, but they don't have the financial resources to do so, and that we need to provide education for free. Many of us who teach, really, we don't need money anymore at some point, and we are. But of course, Satya was doing it even when he was young, when probably he could have benefited from earning more for his teaching. He still did it for free. That's just very, very inspiring. But I really hope that more people engage in this kind of free service to society, because I think that's ultimately what makes us scientists into human beings. So with that, this is a disclaimer. So in this talk, I will be using some images and quotes. This lecture may go on YouTube or wherever, I don't mind. But not everything is, some of the things I will use might be copyrighted. So in that sense, it's a disclaimer to say that under fair use doctrine, I'm making a small use of several figures, maybe figures, graphs, and so on. Now, I would like to also give you a quote to set the context for my talk. This is from another person who actually passed away very young. She is Mariam Mirza Khani, a legendary mathematician who passed away at the very young age of 40, but fortunately, before that, got the Fields Medal in mathematics, the first woman to do so. And she said, "I like crossing the imaginary boundaries that people set up between different fields, it's very refreshing. I find there's a little sense of humor in this statement, that it's refreshing. She's trying to imply, I think, that keeping boundaries between different fields of knowledge is artificial. These are imaginary boundaries, and that we can break those rules and walk across the boundaries if we feel like. I think Satya would have agreed with this statement. Good. So let me say also that I don't mind being interrupted at any point of the talk by if people have questions. I also will try to keep the chat window open. I'm not actually, yeah, I have it open now. And so if there's a question in the chat and if I see it while I'm talking, I'm happy to stop and address it. Okay. Now the last 120 years has been an era of sensational experimental discoveries in physics. And what happened was that atomic structure was properly understood for the first time. This led to a field called subatomic physics. And then the constituents of atoms, which are the nuclei, became understood also. And then we went to a field called subnuclear physics. So there were two subs here, subatomic and subnuclear. And with this, we were able to experimentally go deeper and deeper into the inside of what makes up matter. Now, subnuclear physics today is called particle physics, and is the field I work in. Now, another thing happened, which I won't be able to give any time to in this lecture. Astronomers learned that black holes were in some sense the most common objects in the universe, after being thought for many decades to be some kind of fiction, which we should not take too seriously. On another side, the physics of materials changed forever with the discovery of new types of materials, semiconductors and superconductors, which have governed almost everything that we are able to do today in terms of manipulating devices, having computers, and much else. There are new kinds of materials people are talking about called topological materials, and I will touch upon those also briefly in my talk. So most of my talk will be about particle physics with a small excursion to talk about some aspects of condensed matter. Now, during this period when all these fantastic experiments were taking place, several theoretical revolutions took place which changed the way we do theory. It was more or less done hand in hand with the experimental developments. Quantum mechanics, I'm sure everyone knows, special relativity also, general relativity, and quantum field theory, which in the condensed matter context is generally known as many-body theory. So these four developments created a totally new level of sophistication in physics, due to which we could answer many questions that people didn't even think of asking before the 20th century. And as a matter of history, correctly, these theories originated in order to explain specific experimental facts. Experiment was moving very, very fast. This is largely because new technology was available, and therefore people could have better microscopes, they could have better telescopes, they could have other kinds of instruments like interferometers and so on. And then theorists were trying very hard to create the theory that supposedly explains this and predicts more results. And they did very well, of course. But today I'm going to argue a converse, which is very curious, that once we have understood the mathematical structure of these theories that I've listed here, it gives strong constraints on what is possible in nature, to a point where experiments can be sort of not just predicted, but even sort of new ideas in a way can be predicted with some level of certainty, even quite radical ideas. And in fact, this sort of mathematical structure in some ways has been more successful than the traditional way of pursuing physics. And I'll try to defend my thesis with a number of examples. Nobody should misunderstand that I'm saying experimental physics is not important. Of course, it's crucial, so is theory. But I think what has happened is that theory in some ways has gone beyond experiment and created a whole new way of doing research. And I think that's very impressive. And I think one should continue along it, even as experimentalists continue to do what they do, which is to discover new facts and verify predictions. Now, I'm not the first to bring up this idea that mathematics is very effective in physics or in natural science. Eugene Wigner in 1959 wrote this article called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And actually, this could be also the title of my talk, except that my talk today is 65 years after Wigner's article, and things have moved very fast. Things that have happened since then and since Wigner passed away also have been quite dramatic. And so things have moved far beyond what he could have known at his time. And in some sense, his thesis has been confirmed over and over again. So in this talk, I will describe how mathematical considerations have led to successful predictions of real phenomena, real world phenomena, over a wide range of sub-areas. And today I'll focus on a few. I'll focus on the discovery of antiparticles, on the field of topological materials, on the understanding of hadrons and quarks, and on the carriers of weak and strong interactions. Now, most of what I'll be saying in this talk is sort of old, fairly old. And I'm also a little nervous because Professor Mani is in the audience, and he is one person who probably knows this history better than I do. And so I'll be happy if he would correct me if I give you some misleading conclusions, or even if I make up history, which I do sometimes. But I threw in this topological materials a little bit because it's a little more contemporary. And of course, there are many things that can be said about developments of the last 20 years, but those we'll leave for another talk, maybe sometime far in the future, because I find that this together makes a fairly coherent story. Now, I say plus black holes if time permits, but time never permits. I have a few slides about black holes, and we'll see. But again, I think that may be a better subject of a different talk, even possibly by a different person in your series. Once I finish giving you a little history, I'll share some thoughts and also a couple of concerns about the way society is thinking about science today compared with how we used to think about science maybe 50 or 60 years ago. Okay, so let's get started. In quantum mechanics, we use a very familiar equation, the Schrödinger equation, to describe the wave function of particles. This is a screenshot from Schrödinger's original paper, and it's the time-independent Schrödinger equation with the terms somewhat rearranged to make it look like a nice differential equation. Now, a glance at this equation tells us that it's not compatible with the special theory of relativity. Mathematically, it is not invariant under a group called the Lorentz group, which is the symmetry group of rotations and boosts, which together form a Lie group called SO3, 1, the Lorentz group. And it's quite easy to see why this equation is not invariant under the Lorentz group, because in the first term, it has a Laplacian, which is only rotationally invariant. And if you perform a boost, this equation will not stay the same. And this was a worry already nearly a century ago, in fact, a century ago practically. And Paul Dirac in 1928 proposed a new wave equation, which is compatible with the Lorentz group. And he used the Lorentz group as the basis for his proposal. He started by asking what we can do with the Lorentz group to find such an equation. And he wrote this paper, The Quantum Theory of the Electron. It's a very immodest title. It doesn't say proposed quantum theory of the electron. And this little bit shows you the kind of person Dirac was. He was quite persistent about his opinions, and he felt that, well, he has found it, and so he will publish it openly under the name that he thinks to be correct. And it turned out he was indeed correct. This is the quantum theory of the electron. I'm showing you a picture here of Dirac in Kolkata, along with Dr. Purnima Sinha, who was S.N. Bose's student and one of the first women researchers in Indian physics. Actually, this picture actually has, I think, S.N. Bose in it also, but I just cropped it to highlight Dirac in India. So what did he do? He derived on his own an important representation of the Lorentz group called the spinor representation and proposed that the electron field should transform under this representation. And this is the proposal that he came up with. This is again a screenshot from his own paper. This is not how the equation is written nowadays. But you see in it some P, so P0 and P3 vector. So these are the 4 components of the momentum 4 vector. And because it has a 4-component vector in it, this equation is able to be Lorentz invariant, and it's the Dirac equation. Today, the equation looks different, and just 2 weeks ago, I was in IIT Ropar, and I was happy to see students wearing this t-shirt, and in fact, they kindly gave me one also. So this is how the equation looks now, and what happens is that in this strange symbol called del slash, which has this del which derivative which has a line through it, contains this 4 momentum that was on the previous page. And this is the free Dirac equation. There are more complicated terms that we add to it. Now, what were the predictions of the equation? Remember, he came to it from group theory. So he had to tell us, what does the equation predict? Well, it predicted positive energy states, which he identified with the spin up and spin down states of the electron. But it also predicted negative energy states. And this was a puzzle. But he was not defeated by it. He said, well, if that's what it predicts, we have to find some way to make sense of it. And I've sketched over here what you see in this figure. These crosses are unoccupied states, infinitely of many of them with negative energy, and 2 at each energy, representing the spin up and spin down state of the electron. And just for clarity, I have pretended that the states are discrete. Of course, the free electron can have any continuous value of the positive or negative energy. But the problem is that there are infinitely many of these negative energy states, and therefore the theory seems to be unstable. That's because particles could fall into these negative energy states and it would never end because there are so many of them. So to get around the problem, Dirac proposed that what nature gives us, which we call the vacuum, is not the one I had earlier with all the negative energy states unoccupied. Instead, he said, they are actually all occupied. They are already filled. They come to us filled. This is the vacuum, and our life is based on excitations around this kind of vacuum, not the vacuum that is empty. So he proposed that these are all filled with electrons, and it's like a sea. So when we go to the sea, we don't see the bottom of the sea, we see the top of the sea filled with water. And so he says, well, the empty space that we look at is like a sea filled with a water of electrons, and excitations take place over that. Now, an electron can transition from a negative to a positive energy state if I give it energy. So the result of this transition is this picture here, where the state of negative energy, which was occupied, has become unoccupied, and the electron has moved up to a positive energy state. Now, what is left behind is a hole, but it's a hole of negative energy, which means it's the absence of a negative energy state. Therefore, the hole actually has positive energy. Also, it is the absence of an electron, which has negative charge. So the hole has positive charge. So Dirac said, look, lo and behold, there is a state of positive energy and positive electric charge. That's a nice thing to have. We've never seen it before, because actually it has the same mass as the electron, and nobody had seen such a particle of positive charge with the same mass as the electron. Yes, thank you. I am getting a request to talk about black holes before going to other topics. Good. So in that case, what I will do is I will cut out some part of my talk and go to black holes, and then we'll see where we get. Yeah. But first, I'll discuss 2 topics, this positron and topological insulators, and then we'll go to black holes from there maybe. Okay. So good. So what does this hole do? I said it behaves like a positron. And although it was never seen before, Dirac said, well, it should be there. Somebody should look for it. And he also said electrons and positrons have to be created or destroyed in pairs because this process which I've sketched here creates both a positive energy electron and a positive energy positron. So they're created or destroyed in pairs. It sounds like a fantasy. It sounds like somebody did some mathematics and now they're insisting that this should be true in nature. Well, in 1932, Carl Anderson discovered positrons in cosmic rays, and indeed they have the same mass as electrons, they have positive energy, and they have the opposite electric charge, namely positive charge, just what Dirac predicted. Today, we know many other forms of antimatter. Beyond anti-electrons, we know anti-muons, anti-quarks, anti-neutrinos. And so the whole concept of antimatter was born by looking at this, trying to look for a relativistic wave equation. And I'd like to actually digress here to point out that there's a very important medical application of this, of positrons, which is called the positron emission tomography. It's a modern tool to carry out a full body scan. And some of us who are quite old might have occasion to have it. I actually had this scan a couple of years ago as a preventive. And what it does is it looks for inflammations in the body that could signal various issues from heart disease to epilepsy to cancer. And it's considered state of the art. So the patient is injected with a tracer that emits positrons. The tracer goes and settles in some areas of the body where the tissue is abnormal, and then the body is scanned to see where the positrons are coming from, and that allows us to reconstruct the original location of these abnormal tissues. So the emitted positrons exactly follow Dirac's process. They annihilate against electrons, and then we get photons back to back, and we get 3D imaging of the body. Who could have imagined that representation theory of the Lorentz group would be behind such a potent tool to diagnose diseases? And I'm mentioning this here. Oh, sorry. Yes, you're right. I was doing that to see my other screen better. Actually, I'm trying to see where I'm not able to see myself anymore for some reason. Let me just fix that. Thank you for telling me. Yes, I think I'm okay now. Screen sharing stopped. Okay, my mistake. Oh dear. What happened? Yes.
You can share again.
Yeah, I will. I'm really sorry for that mess. Okay. I think we're back. I won't move the screen and the camera anymore. Good. Okay. Interestingly, Homi Bhabha wrote this paper precisely on Dirac's process, where electrons and positrons scatter, among other things, by annihilating into a virtual photon. This is something also to keep in mind. So I was saying, the reason to point out this technology is because nowadays we hear a lot about the importance of doing applicable science, because science must be applied for the betterment of society. I fully agree with that statement. At the same time, we must realize that you cannot make up science out of thin air. And it is the fundamental science which was developed by fundamental scientists, which eventually led to this application. This is something which I talk about on other occasions and which I'm very passionate about, that it is fundamental science which has given us the most effective tools to benefit society, and that de-emphasizing fundamental science in the modern era would be a very big policy mistake, which in my opinion, governments all over the world are making. Okay, I'll get off that topic now and continue with my talk. Let's talk about something more modern, and let's get into it right away. So it was believed, this logically connects to antiparticles. That was my thought process to bring up this topic. After antiparticles were discovered, it was believed that all fermionic particles have their own antiparticles. But this was questioned by a young Italian physicist, Ettore Majorana, who proposed that there could be a neutral fermion, uncharged fermion in nature, then it could be its own antiparticle. It might not have an independent antiparticle. Now, this was again a problem in the representation theory of the Lorentz group. And the question was, is there a representation of this group, which is a spinor, which is self-conjugate under charge conjugation? That is the technical word for saying that it's its own antiparticle. And he found this representation. It's called the Majorana representation. And due to this, he proposed that such particles are called Majorana fermions. To date, no such particle has been seen, at least in particle physics. But I mention this for a reason which I'll come to in about 2 or 3 slides. Instead, I'll go on to talk about a few other proposals which apparently failed in particle physics. So here is one. In 1978, now we are coming to much more recent times, Edward Witten studied certain hypothetical particles called magnetic monopoles. Now, these had been discussed as an idea by many people, including Dirac, and he decided to study the field theory of such monopoles in the presence of violation of what is called CP symmetry. C is charge conjugation, P is parity. And in certain interactions, if CP symmetry is violated, he found that there's a new behavior that magnetic monopoles exhibit. Namely, spontaneously due to this breaking, they acquire fractional electric charge, and from monopoles, they turn into dions, which are particles having both electric and magnetic charge. But to date, no elementary dion has been seen. In fact, no elementary monopole or dion has ever been seen, despite quite a few experimental searches. Okay, let me get to the, so this is two failed discoveries. Let me get to the third failed discovery, theoretical discovery. In 1987, Frank Wilczek noticed that in certain models which are inspired by cosmology, by cosmological considerations, and also CP symmetry considerations, the laws of electromagnetism are modified with interesting consequences. And these new laws of electromagnetism come by an extra term in Maxwell's equations. And so this new theory, which generalizes Maxwell's theory, is called axion electrodynamics. For the experts, it basically adds an E dot B type of term to the Maxwell system, and it results in small changes, but significant changes in the equations. But of course, despite a lot of experimental searches, no elementary axion has been seen. So in these 2 slides, I've shown you that the prediction of Majorana fermions, of elementary dions, and elementary axions all seem to have failed. I say seem to have because we cannot give up, but for the moment, particle physics has not found any of these things. However, I'll argue that they were not a waste of time, these ideas. And the reason is that all these concepts, which failed in the context of particle physics, have been realized in novel materials called topological materials. The key property of topological materials is the existence of special surface states. You can see in the figure on the right side that there's a cube, the first cube. It has a gray interior and a golden exterior. And for topological reasons, the behavior of the interior and the boundary are different. So on the boundary, it can conduct, but inside it insulates. So that is a typical example of a topological insulator. And you may ask, well, I can make one by taking a block of wood and pasting some aluminum foil over it. Then the boundary will conduct and the bulk will not. But that's not the same thing. It's intrinsic to the material. I haven't added anything to the material. It's one material. If I slice it in half, the new boundary created by slicing will again become conducting. So it's quite a revolutionary idea. And people in condensed matter physics are justifiably very excited about such materials. Now, the interesting thing is that not very long ago, about 15 years ago, a paper was published arguing that in a certain class of topological insulators called TRI, the analogs of Witten's dions and Wilczek's axions are actually seen. So this is quite a remarkable fact. What these authors showed is that an observable called magnetoelectric polarization in these topological insulators plays the role of an axion. So it's like an effective excitation of this condensed matter material. And the magnetoelectric polarization precisely behaves like an axion, and the system obeys the laws of axion electrodynamics discovered by Wilczek. Now, if you can induce a temporal gradient, that means that this magnetoelectric polarization is allowed to vary in time, then it induces what is called the temporal magnetoelectric effect. And in presence of this effect, magnetic excitations satisfy precisely Witten's formula for dyons. So you see that the axions and dyons proposed in high energy physics have reappeared in condensed matter physics as effective or emergent excitations of such special class of materials. This is a very important lesson. It shows that theory isn't limited to the system that it's developed for. There are some larger rules of theory which make it crop up in different places. And at the end, I'll say a few words about that. So here's a popular article that was written in 2008 to celebrate this paper, which I just showed you. It says, it appears that the same physics of axions in a different context applies to an unusual class of insulators. And the author concluded that these developments have propelled axion electrodynamics from an idle curiosity to an experimentally observable reality. And I will take issue with the use of the word idle. Curiosity is never idle. I think anybody who has worked in theoretical physics would agree with this statement. Curiosity is not idle, and this development precisely shows that. It shows that when you have done something theoretical, which is good, which is solid, which is difficult, which is rooted in the mathematics of the system, you have a chance of realizing it in more than one way. In fact, even Majorana fermions have been claimed to be detected as the surface states in a topological superconductor, also a topological material different from the one on the previous page. However, in this particular, so there's some zero bias peak over here in these graphs, which supposedly is interpreted as a Majorana fermion excitation. Now, the problem with this experiment is that people agree with this graph, but they don't necessarily agree with the interpretation. So it remains somewhat controversial whether Majorana fermions have been discovered, but it's a hot topic and we read about it almost every day in the popular science press and in the technical journals as well. Now, why is this interesting? Well, it turns out that topological superconductors with these Majorana excitations, if they satisfy non-abelian statistics, could realize a type of quantum computing called low decoherence quantum computing or topological quantum computing. The status of this subject is unclear in 2024. It might become clear next year. It might not. We don't know where it will go. But I do want to emphasize that a set of particle physics proposals now makes up an important theme in condensed matter physics. And this is part of my argument about the remarkable outcomes of mathematical physics. Okay, so that concludes my discussion of topological insulators. I have a question in the chat about quarks. I would be happy to answer that, but not now because I haven't spoken about quarks yet. However, if there's any question about either antiparticles or about topological insulators, which actually I'm not an expert, frankly, but I'll be happy to take such questions right away if there are any. Please put them in the chat if you like. I don't see any other questions in the chat, so maybe I'll go on, and then if questions come up, I'll look into them. Okay, so now at Professor Mani's request, I'm going to bypass this and go straight to a later part of my talk, which is on black holes, because yes, of course, that's a very interesting topic. And I will come back to this if there is time. And I think the organizers should tell me if and when there is time. So I hope you can see this screen now. I'm on the black holes page. All right?
Yes, sir. Good able to see you, sir.
Very good. Okay. So, well, the story of black holes started in 1916. Yeah, there is a question on topological superconductors. Can they be used as qubits? Yes, I believe that's exactly the proposal of these topological materials, that their excitations can be used as qubits. And the idea is that they will have low decoherence. That means that the entanglement based on which we do computation in a quantum computer will last for a long period of time without being destroyed by the environment. And why? Because the topology, which gives rise to this unusual behavior of these materials, will protect it from decoherence. So that is the idea. It's a lovely idea. Whether it is true, okay, we don't know, but I didn't want to give a talk where I only talk about something from the 1920s, which worked very well. So I threw in this particular discussion to stimulate you that something will happen in our lifetime in the next few years. And I do believe it will. Thanks for that good question. Okay. 1916, Karl Schwarzschild proposed, or actually discovered a classical solution of Einstein's equations, which has a mass or seems to have a mass. So he called it on the gravitational field of point masses in Einstein's theory. And remember, this is just 1 year after Einstein wrote his theory. It's practically one of the first papers on his theory at all. And this is a period, this is in the period 1914 to 18, which I believe is the First World War. So there's quite a lot going on, especially in Europe. And here was this person finding a classical solution that would live on and become legendary for more than a century later. Unfortunately, he himself went to fight and was killed a year, I think, after this paper, a year or two after this paper. So he himself passed away young and never got to see the result of his work. What did he actually find? Well, this is how we write it. So the left side of this equation, ds squared, is the invariant distance or space-time distance of an event which occurs in a coordinate time dt and a coordinate distance dr, d theta, d phi. And instead of just being the usual space-time distance, which should be dt squared minus dx squared, it is distorted by these functions 1 minus 2 gm over c squared r, where g is Newton's constant, m is the mass of this mass point or whatever distribution you want, c is the speed of light, and r is the radial distance to the center of this distribution. And as I said, for decades after this, people thought that this is some solution. Sure, it describes the gravitational field outside such bodies in vacuum. But if you stare at it, any student can see that there is a value of r for which this bracketed function vanishes. And that's very disturbing, because then a tiny interval of time has no impact on the space-time distance, because the first factor goes to 0, and a tiny interval of distance, of radial distance, has infinite impact on the space-time. It's very bizarre. And people didn't believe any of that. They said, no, r cannot be equal to 2 gm by c squared. R should be very large. Then we believe this solution is the analog of the electrostatic field of a point charge. Okay, if I have a charge distribution, we know that the field outside at large distance is radial, but we don't necessarily know what happens inside unless we know what the charge looks like. It might be a distribution, and then we don't know more about it just by solving the equations outside. And that is what Schwarzschild did. But deep inside, as you can see from this, there is a problem. So first of all, at r equals 2 gm by c squared, this thing behaves strange, as I just told you. It gets even worse at r equals 0, where everything blows up. Okay, these denominator, r is in the denominator, so these ratios, 2 gm upon c squared r, just diverge. What does that mean? Well, people call it a singularity, and it's a subject of hot debate nowadays, what it actually means. Okay. Now, actually, there was a sort of gap of about 20 something years when nothing much happened, except that the world was convulsed with a lot of social upheavals. And it was Oppenheimer and Snyder in 1939 who argued that spherically symmetric matter will collapse to such an object. And when it does so, there will be a one-way horizon sort of covering this collapsed object. And because it's one way, things can only go in but not come out. And because of that, the singularity, which is deep at the center of this, will not even be visible to us. Let's say we hypothetically go past this horizon. Well, we might experience the singularity, but we can never come back and tell anyone because it's a one-way horizon. So as long as we stay outside, we don't need to worry about the singularity. Now, the argument was very important, but the weak point was the assumption of spherical symmetry, because as we all know, no matter is ideally spherically symmetric. There will always be some distortions, and in astrophysical processes, involving collisions of planets and stars and so on, there are perturbations. Nothing is perfectly symmetric. And so things are lumpy and bumpy, and there's no reason to believe that Oppenheimer and Snyder's mechanism will apply to those objects. However, the objects were interesting to a few people who had an eye for these curious things. They just kept their minds open. And particularly in Britain, for various reasons, one of which I think is Sir Fred Hoyle, who was of that generation, one of the most inventive people and prepared to pursue crazy ideas. The solution was later interpreted as a space-time from which nothing can escape, and therefore it was named a black hole. Black because things are not black when they emit light. A thing that never emits light is perfectly black, never emit, not even reflect light. So that's what this object was called, if it exists. Now, the physics community, as it always does, was very quick to poo-poo this whole idea. They were like, no, this is a mathematical curiosity. Even in my years of graduate school in 1970s, very few people took it seriously. Especially particle physicists did not take it seriously at all. Relativists were a small community that somehow talked only to each other. And so, as I said, Fred Hoyle was the exception. He even thought, and rightly as it turned out, that newly discovered quasars, quasi-stellar objects, may be black holes. But what remained very unclear was, do generic stars form black holes? That is, are they generic, or do we have to wait for a 1 in a billion chance for a black hole to form? Are they very rare? Are they very common? And that all depends on how likely they are to form. And this problem was revisited in 1964. Now look at the timeline. 1916, Schwarzschild. 1939, Oppenheimer and Snyder. 1964, Penrose. So there are gaps of 20, 30 years between every new development. And that's how times were, actually. And in the 60s, people were busy working, I should say, on particle physics, and not so many people were looking at this kind of esoteric subjects. Particle physics was undergoing a revolution with the discovery of hadrons and the proposal of the quark hypothesis. Let's talk about Penrose. He was actually a mathematician, and his father was also a mathematician. Actually, Penrose all his life has been in a mathematics department. I don't think he's ever been his regular permanent position has ever been in a physics department. And this is one of his first papers, a generalized inverse for matrices. Well, what could be less about physics? His idea was, well, if a matrix has determinant 0, we all know you can't invert it, but maybe you can construct some object which qualifies to be a generalization of this inverse. With his father, they also indulged in mathematical games. And these two so-called impossible figures are part of recreational mathematics. They are a very respected part of that field, and they were proposed by Penrose, Roger Penrose, and his father. If you look at this triangle, you see that the way that the perspective of this triangle looks perfectly reasonable near any of the three corners. But when you try to continue it, to the other corner, it looks nonsensical. The white line at bottom left, it looks to be behind, but now on the top, has come on top. Okay. And so similarly for the gray line and for the black line. And if you look at the staircase, to our eye, it appears, if you start on the extreme left of this staircase and you come towards the right at the lower side, you see that you are climbing, then you're climbing again, then you're climbing again, and you're climbing again, and you're back where you started. This is hilarious. This is simply not possible in real life. It's a trick of perspective. Both of these are just tricks of perspective. And in fact, they corresponded with a Dutch artist called Escher, and he did a painting which is quite famous called Ascending and Descending, which shows some figures wearing helmets looking a bit like soldiers, just steadily climbing the staircase, which actually now in this figure goes up towards the left. And then they climb and they climb and they climb and they are back where they started. So it's an artistic representation of Roger Penrose and his father's little tricky drawings. But then in the 60s, Penrose became interested in a physics question, and in fact in Einstein's equations. He studied exactly the Oppenheimer-Snyder problem, which is how do collapsing objects actually collapse? What is their time evolution? And this is a diagram from his paper, which, by the way, his paper is only 3.5 pages long. It's very difficult paper. I think there are very, very few people in the world who could say they understand it really well. But in the last few years, I put my mind to it, and I think somehow I have a slight grasp of what is going on. So just to follow this figure, you should think that time is going upwards, and all the circles in this figure are actually spheres. Okay, you can't draw a sphere on along with time very easily. So he drew it as a circle. So at the bottom of the figure, there's a large circle. And as you go up in the figure, this circle is collapsing. This is the inward collapsing shell of matter. But now you see there's a ring drawn somewhere at a point, at some point of time, a dark ring. And this is a special kind of surface called a closed trapped surface. It's characterized by some rather sophisticated mathematics. And what he showed is that if this surface forms, then the collapse is inevitable. You can poke it this way or that way. You can forget about spherical symmetry. It doesn't matter. It's not necessary to have been spherically symmetric for this procedure to happen. And this was the essential new contribution of Penrose, that gravitational collapse to a black hole is a generic and not a very special phenomenon. Okay, and once it collapses to a black hole, then also there's an inevitable formulation of a singularity, which is the vertical black line. Remember, this is a space-time diagram, so time goes upwards. And so this vertical black line is a point in space, which is singular, which just keeps propagating forward in time. Okay, and he's drawn the causal structure of this whole thing. That's subject for a more detailed talk on relativity, but this is Penrose's discovery. And I would say that today most physicists would be unable to follow this 3-page paper. But what I can say with certainty is, if you looked at the subject in the 1960s, most physicists who could not read this paper would say, anyway, it's some fiction. Who cares about these things? And yet, this is a 1960s, early 60s paper. This was its conclusion. Deviations from spherical symmetry cannot prevent space-time singularities from arising, which is saying that a black hole will form. They will form repeatedly. And Penrose came to this conclusion. These are his own words that I've copied from his paper. So a variety of stars will collapse into black holes with a singularity of space-time at their core. That's the prediction. And in fact, a more general theory than what Penrose could give in his short paper was provided together by Hawking and Penrose. And they did a kind of combined study of singularities, both in black holes and also cosmology, which was Hawking's primary interest. And in those 50 years after Penrose's work, from 1960s till the 2010s, black holes went from being a mathematical curiosity to, in some sense, the most common objects in the universe. And Today, there are estimated to be at least 10 to the 11 supermassive black holes, each having a mass 10 to the 6 to 10 to the 9 times the mass of the sun. And in addition to these, there are black holes with the mass of the sun or 10 times the sun, 100 times the solar mass, and they are everywhere. And every day, LIGO is observed, every day or every few days, LIGO is observing the gravitational wave signal of the mergers of such black holes. And they can work backwards and estimate the mass of such black holes. And the typical ones found by LIGO are like 50 or 100 times the mass of the sun. So they really are common. And the Nobel Prize in 2020 went indeed to Roger Penrose, as well as the two astronomers who played a key role in discovering one black hole, the one which is at the center of our galaxy. So this was the prize. And note that half the prize went to Penrose, the other half was shared equally by the observational astronomers, as often happens, because one took care of the theory single-handedly, and the other two got sort of shared credit for the observation. Now, this was the end of my talk. It's not the end of the present talk, but it's the end of my discussion of black holes. So again, I will, interrupt my screen sharing, and I'll pause for questions. But after the questions, I will tell you something about hadrons and quarks. So let me go there. And now we can pause for questions. So I see that there are a few questions on topological materials. Do they have to be synthesized artificially or in nature? So many topological materials are intermetallics. That means it will be rare to find material. Sure, it will be rare. You know, I cannot probably in this talk, I cannot give you those details. What I can tell you is only the reference of this paper. And I think you should go back to this paper for the details, the TRI insulators paper. It is by Xiaoliang Qi, Taylor Hughes, and Shucheng Zhang. And these are the people who wrote this. It is published in what? It's a physics viewpoint. So it's an article in this collection, Physical Review B 50th Anniversary Milestone. So if you Google Physical Review B 50th Anniversary, I think you'll find this paper in the milestones. Now, about black holes and information, that's a nice question. Again, you know, unfortunately, so much is happening in this field that I cannot give you a quick answer. One answer, logical approach to this would be to discuss the entropy of black holes, which actually would be a very good follow-up to Deepak Dhar's talk on entropy, and which would again address the latest developments on the field of statistical physics, which is the fact that black holes appear to carry an entropy. So I would actually propose you get somebody. If you're lucky, you can get Ashok Sen. Can you excuse me for a second? I think my doorbell is ringing. I need to just check it. I'm really sorry. Okay, no, I was wrong. All right. So the relation between black holes and information is the fact that black holes carry an entropy, and that without that entropy, the laws of thermodynamics are not correct. This is a major contribution of Stephen Hawking. And because of that, it raises questions about whether information is conserved, because when black holes evaporate, apparently they seem to take away whatever information was inside them. Hawking showed that they evaporate. And this has led to various paradoxes, and there are many theoretical efforts today to understand what happens to the information inside a black hole when it evaporates. So that's my answer to Professor Mani's question. There's also a question, what was C.V. Ramanujam contribution for black hole? No, this I do not understand. Who is C.V. Ramanujam? I don't know this person.
I think he might refer the Vishweshwaraya, I think so.
Vishweshwaraya. Yes.
Black hole person.
Okay.
That's what he means. Maybe.
So Vishweshwaraya, of course, Vishu, as he was known, played an important role in suggesting how gravitational waves could be discovered. I would say that, C.V. Raman. No, C.V. Raman did not, I believe, have anything to do with black holes at all. Abhilash, these sort of general questions, I think what you should do, and I mean it very seriously, go to Wikipedia and go to the page on quantum computing, also go to the page on C.V. Raman, also go to the page on black holes. I think these will stimulate your curiosity. And, Wikipedia, we kind of think it's just something out there, but it's a very valuable free resource to understand the beginning of the subject. Once you understand that, you will find some references there and you will be able to look into more details. So there are many levels of learning these things. Even for a person who is not, so you are in computer science, there are popular science books which explain C.V. Raman's work, that is work on molecular, basically spectroscopy. So that is nothing to do with black holes as far as we know. Quantum computing is a whole other subject, also nothing directly to do with black holes. It is based on quantum entanglement. And then, of course, there is black hole physics. So these are three quite distinct subjects, but there are some, as Professor Mani pointed out, there is some relation between information and black holes. And this relation brings in the concepts of quantum entanglement. Now, it is 7:15 and I should ask the organizers how much longer they want me to talk. If at all, I can stop here.
Yeah. No, sir. You can go for another.
Joseph, I'm sorry, I'm not able to follow what you're saying. I think maybe my
No, it's fine. It's
but-
fine. If you want to talk about some amount of hadrons and quarks, that's fine, I think.
Okay. So maybe I will talk for about 5-10 minutes max.
Yeah, it's perfectly fine. It's
Okay.
perfectly fine.
Okay, then I'll cover this history. This is a history I think that Professor Mani is intimately familiar
Yes,
with,
yes.
but I'll give you my little take on it. That's all. Again, it's one more of those examples which tells us the power of mathematical thinking and leads to very important outcomes. At the end of that, I can answer the question I was asked about experimental, why are quarks not observed? And let me tell you right now, quarks are observed. So I'll explain all that. Now, here's the situation in the 1950s. Experiments are getting better and new particles are being discovered in experiments. They're strongly interacting. And because the energies that we can access in experiments are getting higher and higher because of better technology, we are able to create these new particles. The particles were always there in nature, but we never knew them. We had never seen them. Now we are able to create them and detect them. So therefore they exist. But, already we knew of electrons. We already also knew of the mu meson or muon. But now what are all these so many hadrons? We know of protons, we know of neutrons, those are hadrons. We knew of pions. But what are all these new hadrons? So many of them. Are they elementary or are they made up of something else? Why are there so many? And in 1961, Murray Gell-Mann and independently Yuval Ne'eman proposed a classification scheme for these new particles based on the representation theory of a group called SU3. This is not the Lorentz group SO31 that I discussed earlier, but it's another Lie group. If you know enough about Lie groups, you would know the classification, and SU3 is one of the simpler ones. Not the simplest, but among the simpler ones. Now, SU3 can be thought of as a Lie group or a Lie algebra. It's simpler to think of it as an algebra, and actually that's what physicists use most often. It generalizes the familiar rotation algebra based on SU2, which, as we all know, is generated by the Pauli matrices. In fact, Gell-Mann wrote his own matrices called the Gell-Mann matrices to describe SU3, although mathematicians knew that much before. Now, a representation is an abstract concept. It's a vector space where the symmetries act as matrices, and in this case, as unitary 3x3 matrices. Now, it was known at the time that neutrons and protons satisfy an approximate isospin symmetry, which fits with the group SU2, which is a group of complex rotations in two complex dimensions, which are spanned by this abstract field of the neutron and the proton. But what Gell-Mann and Neyman noticed was that there seemed to be stronger mathematical rules for SU3 representations. And if you invoke those, then these new baryons and mesons, which kept coming out of experiments, seem to follow these new rules. And Gell-Mann described it in his preprint called The Eightfold Way, A Theory of Strong Interaction Symmetry. But this remained only an internal note circulated within Caltech. The 8 in eightfold way comes from the fact that the dimension of SU3 is 8. Okay, but the eightfold way is the way described by the Buddha to understand reality through Buddhist principles and meditation. Gell-Mann was a student of many cultures, world cultures, and he had come across this Buddhist eightfold way, so that he gave that name to this. Now, here is one of his observations. He said, look, we know the neutron and the proton, but we have now discovered new particles in recent years called sigma minus, sigma 0, sigma plus, psi minus, psi 0, and lambda. And look, if I put all of them in a hexagon such that 6 of them are on the vertices and 2 are at the center, this is actually a diagram of the SU3 Lie algebra, where the central 2 dots correspond to the Cartan subalgebra, and the 6 vertices of the hexagon correspond to roots, simple roots of that algebra. And he said, well, if I do that, see how neat it is, because the isospin varies from left to right. So neutron has minus half, proton has plus half. The strangeness, which is a quantum number of these particles that was assigned, varies from the top going down. Neutron and protons have no strangeness. The sigmas all have strangeness -1. The psis all have strangeness -2. And if you go along a diagonal axis, which is like the bottom left axis of the hexagon, and you translate that way, then the electric charge goes up from -1 for sigma minus and psi minus, then 0 for neutron, sigma 0, lambda, and psi 0, and then to +1. So he says, look, these are all group theoretic properties of SU3, and these particles fit it. And note that all these particles have masses in a similar range, 940 to about 1350 MeV. So he said this is a symmetry of nature. Now, there are many different representations of SU3, and the simplest ones have dimensions 3, 8, and 10. This I can't derive for you, but it's a simple thing to derive if you study Lie algebras. And he noticed that the 8 and 10, which he called the octet and decuplet, kept fitting all the new mesons. This is the one I showed you, is not the only diagram. It kept fitting all the new mesons, but leaving some gaps. For example, there was a meson octet which had 3 pions and 4 K mesons, but an octet is supposed to have 8 particles, or supposed to have 8 dots, as I showed you in the previous slide. But here are only 7 dots. Where is the particle that completes it to 8? And he said, well, if it's not known, it must be there, and we haven't found it. And so this is a screenshot from his own paper, from his own internal note. He said, the most clear-cut new prediction is the existence of chi 0, what the name he gave, which should decay like this unless it is heavy enough to decay like that, etc., etc. He gave a lot of details about, qualitative details about what it should do. Now, this particle, now known as the eta meson, was discovered later the same year, and it had exactly the properties that Gell-Mann predicted. But unfortunately, Gell-Mann had not published that internal note. It was only circulated within Caltech. And so his prediction was not properly acknowledged, and people were not in their minds clear that Gell-Mann had really predicted the eta meson. It took some time for them to accept such a thing. And in my view, this is because of this outlandish idea of trying to predict particles from some group theory. Although Dirac had done it, but this was a new kind of group theory applied to internal symmetries. People were simply not getting used to this idea. So Gell-Mann said, okay, you don't believe me, I'll do it again. So in 1962, he did it again. He grouped, I'll show you the figures in a moment. He grouped a set of known baryons into this decuplet, 10-dimensional representation, and again found one missing. And he predicted the omega baryon and its properties, and he published it. He said this baryon will have strangeness -3, electric charge -1 unit, mass of about 1680 MeV, and this particle was found in 1964. Now, there was a 2-year gap, and in these 2 years, people knew that this Gell-Mann guy is predicting stuff, and then he's claiming that his predictions are verified. So people literally knew that he had predicted this. Now, there were other people in the field, and I don't want to minimize their contribution, but Gell-Mann's predictions really turned out spectacularly successful. And let's take a look at the figure. So on the top left, we have the meson octet, and this eta you see sitting at the center, this was not known when Gell-Mann wrote it. He said there should be such a particle. The other 7 particles were known. And he said, well, look, SU3 doesn't have a 7-dimensional representation. So if my ideas are true, there must be an 8-dimensional representation of which these 7 particles are a part, but the one is missing. And he predicted the eta. And because it was missing from the center of this diagram, he could tell you the electric charge, the strangeness, and the isospin of this thing. All 0, actually. All the electric charge, strangeness, and isospin are all 0. For the decuplet, he knew the deltas, he knew the sigma stars, he knew the psi stars. These are 9. These are 4 plus 3 plus 2, 9. But the decuplet diagram taken from Lie algebra theory, representation theory, is a triangle with something at the bottom. And this bottom particle, omega minus, wasn't there. This is what he predicted. And it turned out right. And omega minus indeed has strangeness -3 and electric charge -1 and isospin, I guess, 0. Isospin is from left to right. Yes, 0. And that's what it is. And it was found. So these are the 2 new particles he predicted successfully using group theory. Now, Gell-Mann didn't end there. He continued to think about this problem. And his conclusion was that, look, I found many things in the 8 and 10-dimensional representation, but group theory tells us that these are nothing but products of a fundamental representation, which is 3-dimensional. So wouldn't it be nice if there would be particles in this 3-dimensional representation? Then all hadrons within this 8 and 10 and so on would be their bound state. And so he again made a prediction inspired by mathematics. He said, and independently George Zweig, that there are constituents of hadrons called quarks. And the proposal was that there are 3 particles called up, down, and strange quarks. They have fractional electric charges like this in units of the electron charge. And all baryons, which have half-integer spin, are bound states of 3 of these, while all mesons, which have integer spin, are bound states of a quark and antiquark. The proposal fell into place beautifully. It could explain all these representations that he had already discussed. But it gave some new predictions. For example, if we try to bind one quark with an antiquark, we get 9 possibilities. UDS bound with U bar, D bar, S bar. Now, 9 particles is 1 more than the meson octet. So there's a 9th particle. SU3 group theory doesn't say there should be a 9th particle. It says that if the octet occurs, it should occur as a whole. The singlet, if it occurs, can occur, but it doesn't say both should occur. But the quark model says both should occur, because now if you have bound states of these quarks, why shouldn't we have a bound state for the singlet? And in fact, this new meson, the eta prime, which is a direct prediction of the quark hypothesis, was discovered in 1964, and it's the 9th meson in this list, of which 8 were known. And now the quark model was met with great skepticism from both theorists and experimentalists. Actually, you cannot imagine the amount of negativity in the 1960s literature about this model. Many people said, well, it's just some mathematical way of organizing, and they all had this question, if there are quarks, why have we never seen them? They have fractional charges, they should be easy to observe. Well, the question was settled in 1968 when an experiment, or actually series of experiments, showed that if I hit a proton hard enough, then my probe will go inside the proton and will reflect from very hard constituents inside the proton. And unambiguously, it shows that the constituents of the proton are quarks. So there is no question at all about their existence today. They do exist. and they sit inside protons. The only question is, why can we not knock them out of a proton? That's the statement which today people sometimes understand as quarks are not observed. They are not observed as free particles, but they are very much observed sitting inside protons, neutrons, and all these other mesons and baryons. Even at this time, physicists were reluctant to agree that these are the quarks that Gell-Mann proposed. Feynman invented a new name for them, partons, and he argued a few times that maybe partons are not the same thing as quarks. Partons are the constituents of protons and neutrons, but the group theory stuff that he didn't like somehow. Eventually, it became clear, and today it is everybody agrees that these partons, these are the same as quarks, and quarks absolutely do exist. So this is the sort of conclusion of Gell-Mann's work. And again, there were other people involved. Maybe I've highlighted Gell-Mann too much, but he was a very, strong believer in this sort of way of thinking. And eventually, it also became clear why quarks are not seen freely propagating. It's because they are permanently confined by the dynamics of quark interactions. Good. So that is the end of that, and that's also the end of my talk. So I'll stop here and then I'll answer questions. So thank you very much. Let me get to the questions. Schrödinger initially was writing a yes, Klein-Gordon equation, absolutely. Schrödinger's, I think, I think both of you are correct. Sommerfeld suggested to Schrödinger to try out a relativistic equation, I think what he meant. And indeed, the Klein-Gordon equation was known, but that could not describe electrons because it describes spinless particles. It describes bosons, while electrons are fermions. So in a way, if we had to rewrite history, it may not have gone that way. It is true, though, what Dirac found is true, that for fermions, you need this spinor representation. And when you use it, the simplest spinor representation satisfies the Dirac equation. There are also more fancy equations for spinors, but with higher spins like 3/2, 5/2, and so on. But for spin 1/2, the Dirac equation is the right one. Meanwhile, even Dirac knew about the Klein-Gordon equation, and that equation only became really relevant in particle physics after people discovered the Higgs boson, because the Higgs really satisfies the Klein-Gordon equation. It's a scalar particle. So indeed, both equations are important, Klein-Gordon and Dirac. And there's a third class of equations, the Yang-Mills equations. And between these three equations, we have all the equations we need to describe all known elementary particles. I hope I've answered the question about existence of quarks. This experiment shown on the right over here is exactly the experiment that detected quarks. Okay. I'm being asked, thank you, Dev Shankar, for your kind comments. Ritish wants to know a book for pure maths, topics like function. Well, for a physicist, okay, well, as it so happens, I have a book which I co-wrote with Professor Mukunda called Topics in Differential Geometry, Topology, and Group Theory for Physicists. It's actually two half books, one half I wrote, one half Professor Mukunda wrote. They are relatively simplified expositions of the subject for physicists because we've presented the essential ideas without going into the rigorous proofs. It is the rigorous proof which is a kind of block for physicists to understand mathematics, in my opinion. It's important. Mani, thank you. Page curve. Unfortunately, not with the material I've talked about today. I cannot really explain. Okay, let me try. Let me try. So coming back to the book, though, this book by myself and Mukunda is probably, I don't think it's easily available, but you can download it from anywhere. And if you can't, just send me a mail and I'll mail it to you. Okay? It's really not a problem. I'll mail you the whole PDF. It's not even a very big file. Page curve. So the idea of page curve is the description of where the information lies when a black hole emits. So a black hole, through quantum processes, emits particles, and by emission, it evaporates and becomes actually smaller. And the page curve quantifies the fact that as the emission goes on, the amount of information that comes out increases. But as that happens, the black hole becomes smaller and smaller, and clearly it has less information inside it. It can't keep on emitting information forever. So there must be a point where the information that it's emitting starts to decrease with time instead of increasing. And so this curve which goes up and down is called the page curve. And now there are theoretical models where you can actually try to reproduce this curve by studying the evolution of black holes using this so-called ADS-CFT correspondence. Yeah, that's the correct book, Dev Shankar. Yes, that is the book. And please share, please feel free to share it widely. Okay.
Any other questions? Please, you can also unmute yourself and ask.
Yes, please do that.
Feel free.
Okay, I think it's quite late for everybody, so maybe we should just end here.
Yeah. Thank you, Professor Sunil Mukhi.
Thank you all. Thank you for inviting me, and it was really a pleasure to be.
Thank you very much. It's a wonderful talk.
Really a pleasure to be here and to interact with all of you, and I'll be happy to do so again. So thank you all.
Joseph?
Right.
Yeah, somebody's going to conclude, right?
Yes, sir.
Yeah,
Sir,
Sitikant, please. Yeah.
Yeah, sir. Good evening, everyone. I am Sitikant Mishra, Satyasar student, now working as a reactor physicist at NPCL Kodamkulam. On behalf of all the Sunday class students, I would like to extend our heartfelt gratitude to each and every one of you for gracing this seminar with your presence today. First and foremost, our deepest regard goes to our esteemed speaker, Professor Sunil Mukhi sir. We are truly honored to have the opportunity to listen to your insightful lecture on the remarkable outcomes of mathematical physics. Sir, your depth knowledge and lucid explanation has left an indelible mark on all of us. Your lecture reminds me of Eugene Winger's paper on the unreasonable effectiveness of mathematics in natural sciences. Sir, you have shown that paper today. Thank you for that, sir. Thank you, sir, for clearing all our doubts during question answer session. Sir, we are really grateful for your illustrative talk and your valuable time. We would also like to express our sincere thanks to Professor H.S. Mani sir for his dynamic and effective participation in organizing this lecture series. I also thank him for his valued lectures in Sunday classes. Hearty thanks and appreciation for all my teachers, Professor Kamleskar sir, Professor Rajsekharan sir, Professor K.P.N. Murthy for their inspiring efforts. I thank all the organizers, Joseph sir, Kamal sir, Rubala ma'am, Aswil sir, Preeti ma'am, Ayapan sir, pardon me if I forget any name, who have worked tirelessly to make this lecture series possible. I would personally like to thank Joseph sir for his effort in popularizing science. Here, I like to mention that Professor Kamal sir is now teaching online every Sunday. I request every student to take advantage of this opportunity and make use of it the most. Furthermore, we would like to extend our gratitude to all the attendees for your active participation and engagement throughout the seminar. Your thoughtful questions, comments, and discussion have added immense value to today's program, and we appreciate your enthusiasm for the subject of physics. In closing, let us carry forward the knowledge and inspiration gained from today's seminar and continue to explore the wonders of physics with curiosity and passion. I think that would be a true homage to our beloved Satya sir. Once again, thank you all for your presence and participation. Wishing you all continued success and advancement in your respective endeavors. Thank you again, sir, Professor Mukhi. Thank you. Thank you all.
Thank you very much.
Thank you all.
Yeah, we formally close now. Thank you all.
Okay. Goodbye.
Bye.
Thank you.